compression members. Now we have already looked at its introduction as to what compression members are and what are the common uh, sections which are used as compression members. Nonetheless, just to give a quick revision, the members that are subject to concentric axial forces. Okay, not just axial forces, concentric, meaning that the axial force or the line of action of the axial force coincides with the axis of the member. Okay, now I'll quickly just.
Bhargav, we can't hear you properly. Your voice is cutting.
Okay. Can you hear me now?
No, it's still
Yes.
cracking a bit.
Yes, we can hear you.
It's okay for me.
Okay. So what I meant by concentric action force. So let us say that you have a rectangular cross section. So let us say this is your column.
Bhargav, sorry, are you sharing screen?
Just a moment. Can you see my screen now?
Yeah, now we can.
Okay, perfect. So let us say this is your cross section of a column or cross section of a compression member, and this is your elevation. Okay, so we call it a compression member when the line of action of the axial force is along the axis of the member. So this is where the axial load should act. Or if you want to look at an elevation, this is where the axial load should act along the axis of the member. Sorry. So this is the longitudinal axis of the member that passes through the centroid of the section. So if and only if the line of action of the force is along this line, only then we call it as a compression member. Now what happens? And this is your line of action of force here at this point. So what will happen is, this is an elevation, and this is the axis of your member. And this is the line of action of the force. So now what happens that in addition to the axial force, there's also a moment, because the section is going to, so we can split this into two components. The first component is the axial load. Now let us say that this is acting at an eccentricity of E. Okay, so the second component is a moment that is equal to P times E. And then such a member, if the moment is significant, such a member is called as beam column. And this member is called as a column or a compression member. Is it clear?
Yes, yes.
Right? Very simple concept. Therefore, it's important that the member is subject to concentric axial force, which tends to reduce its length. Then we call it as a compression member. So since it is under uniform compression, any section, if we cut any section here, that section is going to be under uniform stress. So let us say this is that section. So this section is going to be under uniform stress, and that stress is, let's say I represent it by Fc, which is the stress in compression. This is equal to P by A. Stress is equal to force upon area. Simple. So we can expect all the parts of a compression member to be under uniform compressive stress. Now, in tension member, could you sort of go back and try to remember what factors affected the design strength of a tension member? Anybody? What factors affected the design strength of a tension member? We could start with simpler ones. For example, the area of cross section. Yes, we always, in all our calculations, we had the width of the member, the thickness of the member. If it is an angle member, then we had the gross area, we had the net area. So it depends upon what is the cross section dimensions of the member. Then in all our formulae, we had either the yield stress or we had the ultimate stress. So it depends upon the material properties as well. Then if it were sections like an angle member or channel member wherein some of the legs were outstanding, then we had the effect of shear lag. Okay. Then in some of our calculations, we also had pitch and edge, which is the center to center distance between the bolts. So these are the factors that affected the strength of a tension member. So the factors that affect the strength of a compression member are first the cross section shape, which is common with tension member. But here, in addition to just the area of the section, another parameter that is quite important is the radius of gyration. Now, if you can go back to lecture number 1, we talked about two parameters. One is the section modulus, and second is the radius of gyration. So we said that section modulus is a measure of bending strength of the member. Z, if you remember the notation. So Z, section modulus, is a measure of bending strength. Higher the value of Z, higher is the bending strength. Similarly, radius of gyration is the measure of buckling strength of a member. So higher the value of radius of gyration, higher is the buckling strength of the member. So here, in addition to the area of cross section, the radius of gyration affects the strength of a compression member. Then length. Now, how does length affect? So if in tension members we saw that length did not play any role, irrespective of what the length of the member was, the length of the member never came into picture. But here it does. And I think we already know an answer to this. Why? As to if you take say two steel scales that are of different lengths and you try to load them, it will be it will be obvious that the longer one sort of buckles at a very you have to put in much less effort to buckle the longer one. So even though the section is the same, the material is the same, but only because you vary the length, the amount of axial force that it can take varies, and thus length affects the strength of a compression member. The next factor is end support conditions. Now you again imagine yourself holding that ruler in between your palms and pressing it. So that is similar to a pin-ended or a simply supported condition. Now what you do is you sort of clamp in between, you just clamp it in palms and then you try to compress them. In that case, you'll notice that it will require larger effort on your part, which means that you did not change anything. You did not change the length, the material, or the cross section. All you did is you changed the way you are holding it at the ends. So you basically changed the end support conditions. And then you realize that the amount of effort that you put has changed, meaning that the strength of the scale or the strength of the compression member has changed. Now, obviously, excuse me. Obviously, the properties of the material are going to are going to affect the strength. And the last set of factors, which we did not again have in tension members, are residual stress and various imperfections. Now, we are not going to get into what residual stress is, what imperfections are, but just to name a few imperfections. Now, the vendor that is supplying you the member might say that, sir or madam, our column is perfectly straight, irrespective of which section you choose, I'm going to provide you an exactly straight column. But there are always going to be some, imperfections, so there are always going to be uh, some inherent crookedness that the column might have. Now, I'm exaggerating this, but I just want you to get a feel of it. That this is what the vendor might promise, but this is what you might actually get: a slightly crooked column. Now, this is an exaggeration. Okay, don't take it in this scale. So that's an imperfection. Another imperfection. Now, the structural engineer thinks that the column is going to be loaded like this, exactly along the axis. Okay, but what actually happens, because of factors that were not considered in the design, it is getting loaded like this. Okay, meaning that there is an axial load and there's a bending moment. So this eccentricity was not considered in the analysis. So this is again an imperfection. So there are a number of imperfections like this, which sort of affect how the column is going to behave. So the behavior of column, the reason for mentioning all these factors is to just give you a feel that the the designs, the computing the design strength of a compression member is a very complex process. It depends upon a number of factors, and it's very difficult to consider all these factors and at once and to arrive at a very reason and to arrive at a perfect number, which is it is not the case in case of tension members. We uh, there's no, the end support conditions do not affect it, the length of the member do not affect it, and so on. And to add to this difficulty, there's this phenomenon called buckling. Now we know that compression members have a tendency to buckle. So if it's a very short compression member, for example, you take a 15 centimeter scale and you try to compress it, it might buckle after some time. But you take a 30 centimeter scale, apply load, it'll start buckling. It will start buckling very, at a very less amount of load. So buckling again complicates this process further, and it sort of reduces the amount of load that a column can take, even though the material might not have failed. So buckling is a geometric failure that complicates this process. So common examples of compression members are chord members in trusses. So the top chord and the diagonal chord members are a few examples of compression members. And interior column in buildings. Now I think you already know why I say interior column, because edge columns are likely to subject to axial load and uniaxial bending, and the corner columns are likely to be subject to uniaxial loading and biaxial bending. And that's the reason I say interior columns of the buildings. Then bracing elements. We as of now, we already know that bracing elements can act as a tension member or a compression member depending upon the direction of load. For example, if you look at this figure, if the load acts from in this direction, if the load acts in this direction, then all these are going to be under compression, and all these are going to be under tension. If the load acts in this direction, these are going to be under compression, and these are going to be under tension. So it depends upon what is the direction. So the struts are act as compression member or tension member depending upon the direction of the force. Then these are the typical cross sections that are used as compression members. The most common ones being an I section, then hollow circular section, hollow square, hollow rectangle. And in case we require larger sections, that is, if only a single section is not sufficient, then we build these compound sections, in which again the box section is most common. So one thing that you'll observe in all of this is that in these sections, it is tried that the area should be at as large as a distance from the centroid, meaning that we are trying to maximize the value of R in these sections. Please give me a moment. So just like we did in tension members, we are going to look at various modes of failure, and then we are going to make sure that through our design, we're going to make sure that none of these modes of failures occur. So, would someone would someone like to quickly revise what are the modes of failure in tension member?
Before that, I have a question, Bhargav. So, like, after that, those section yeah. So you were saying that we try to maximize the value of R here, but why are
Yes.
we doing it? I missed it.
Okay. So we
Um,
try. Okay, because see, uh, a generic answer to this is that buckling strength is a function of R. Greater the value of R, greater is the buckling strength. So if I compare two sections, say an I section and a circular section and a hollow circular section, both of them have the exact same area, and I want to sort of identify which of the sections would act as a better, or which of these sections would take a higher action load. The answer would be a hollow circular section because if I look at an I section, so say this is my I section and this is my centroidal axis somewhere here. If I look at a hollow circular section, say this is a hollow circular section and this is my centroidal axis. So in a hollow circular section, almost all the parts of the section are as away from the central axis as possible, meaning that they have a very high value of R. But if you look at an I section, there are many parts which are in the proximity of the centroidal axis, and therefore the value of R here would be less than the value of R here. So let us say this is an I section, this is a circular section. So just by looking at the values of R, I can see that this is a better compression member than this. And that is the reason, and that is the reason why, irrespective of which type of section we are using, we at least make sure that the area is spread out as much as possible. For example, if you use a section like this, a solid circular section, one thing that can be guaranteed is it is not a very efficient way. It is not a very efficient section. You use the same area and then you just convert it into a hollow circular section. This is going to take much higher load than this because now you have distributed the particles at a larger distance from the centroidal axis, meaning that this will have a value of R which is greater than this R. Is it clear?
yeah. Thank you.
Okay, now going back to my original question, modes of failure in tension members. By now you must be, you might be able to solve anything from tension members even in sleep. We've discussed so much about it.
Gross section yielding,
Mm-hmm.
net section rupture, and block shear failure.
Okay, so the cross-section yielding, net section rupture, and block shear failure. The modes of failure in compression members are local buckling, squashing, flexural buckling, and torsion and flexural torsion buckling. It's important that you remember these names. Okay, get into what these are, how to avoid those. It's important that you remember these names. First one is local buckling. Now, when we have a section, say an I section, which is used as a compression member, and it is under compression, means that every component of it is also under compression. So these flanges are also under compression, and this web is also under compression. So it might happen that even though the section as a whole might not be slender, okay, but the component individually is slender. Did you understand what I just said?
No, can you repeat?
Okay, let us just put a sketch to this. Okay, so my aim is to maximize the value of R, for which what I'll do is I will say this is my I section. So my I section has three components. That is, there are two flanges and there's one web. Now, if I look at it as a single section, then it might have a significant value of R, and it might not buckle. But I section is under compression. It itself means that the flange is under compression, this web is under compression, and this flange is also under compression. So if I have to look at only this portion, okay, so even though the section as a whole might not be slender, but a component of it might be slender. So even though the section would not buckle, but this component might buckle. And this phenomenon is called as local buckling, wherein there is no considerable deflection or there's no considerable buckling in the section as a whole, but a part of the section buckles. This phenomenon is called as local buckling. So buckling of the failure occurs by the buckling of one or more individual plate elements, that is flange or web, with no overall deflection of the member. This is called as local buckling. So now the question is how to avoid this kind of a buckling. And the answer is simple. Just make sure that you provide sufficient thickness. What I mean by that is, if you use this section and then you might experience local buckling. A simple thing that you can do to avoid is you just use thicker sections. And you can also, so now the overall area might remain the same, but just by using thicker sections, you're making sure that the individual plate elements or the individual elements of the member do not buckle. Okay. So very simple way to prevent it. Just make sure that there is a sufficient width to thickness ratio. The width is the width of the member and thickness is thickness. So if you increase the thickness, this ratio automatically decreases. So a simple way of avoiding local buckling is sort of a larger thickness, meaning that this width to thickness ratio should be lesser. Any questions here?
So this type of failure like only occurs in an I section, or
It can occur in any type of section that's made up of individual elements. For example, the animation that you see on the right, it's a box section. Okay, so
right.
overall the member is not deflecting, but its individual plates are deflecting. So if you just use a thicker section, it might not locally buckle. So it can occur in any type of section.
Okay, thank you.
Okay, any more questions? Okay. Now, just like we have gross section yielding in tension members, in which the entire section experiences yield stress, but that yield stress is under tension. Okay. Similarly, in compression members as well, the entire section might experience yield stress, but in compression. And this phenomenon is called as squashing. Okay. But there are two conditions for which squashing, if these conditions are met, only then squashing occurs. The first is there should not be any local buckling, because if there is any local buckling, the component has already failed and it cannot really reach its full capacity. So the first requirement is that there there should not be any local buckling. And the second condition is that there should not be any global buckling. Okay, so two things. There should not be any local buckling, there should not be any global buckling, and only then the entire section can reach its yield stress, and only then the column can fail by material failure, or the column can fail by squashing. And the columns which sort of fail by such a phenomenon are called as short columns or stocky columns. And the load at which this failure occurs is called as squash load. Do you understand this?
Bhargav, I had a question.
Yeah.
So only the most efficiently designed columns would fail in such a way, right? Where it's not a failure of the design, but the material itself, and the only way to fix that is to add more material to the column.
No, I wouldn't put it that way. In that way, only the most efficient columns would fail this way. What I would say is simply only very short columns would sort of fail this way. We are going to look at what short columns are and when do we call a column as short. But let's imagine this: if the column is very short, only then, if a column is very short and its individual components are thick or relatively thick, only then it will not buckle. It will not, buckle locally or globally, and only then the material gets a chance to reach yield stress, and only then squashing can occur.
Right, thank you.
We did not have such a condition in tension members. So if it's a tension member, there is no question of buckling. So at some point of time, the entire section is going to reach yield stress. But here, the prerequisites are there should be no local buckling, there should be no global buckling. I think by now you must have understood that buckling sort of reduces the amount of load it can take. So the columns that are long, yes, go on.
Sorry, so does the squash load, will the squash load have a very large value because of the sorry, yeah.
So do you remember we found out the design strength of a tension member under cross-section yielding? That is TDG, right? What is
Yeah.
TDG? It is AC into Fy upon gamma in 0. So even in squashing, the squash load is nothing but area of cross-section multiplied by Fy. Because the way the failure occurs is that the entire section reaches yield stress. So squash load is nothing but yield stress into area. So we want to find out what is the squash load. So force is equal to stress into area. So stress into area. Now which stress and which area? Now we are talking about yielding. So naturally the stress is yield stress, and we are talking about area. So this is nothing but the gross area. Similar to what we had in tension members. So it's not that this value is going to be large, but what happens is because of buckling, our value goes further below this. Now, just to give you, a sense of a feel of numbers, say if I say that if the column is short, it fails at 100 kilonewton. Okay, so let us say that the length of my column was 3 meters. It failed at 100 kilonewton. Now, if I make it slender, so let us say if I make it 6 meters, the same section, the same material, now the column is failing at say 60 kilonewton. So that is what length of the column does to it. It reduces the amount of load that can take.
This is because the 60 kilonewton happens because of the other factors and not because of. So suppose the 3 meter column was failing because of squashing. So the 6 meter won't actually fail because of squashing, but because of probably some other
It will
members.
fail. We are going to look at the third type of failure, and it is likely that it will fail by buckling. And we have assumed that the 3-meter column is going to fail by squashing. So, 100 kilonewton. What I'm trying to say is 100 kilonewton, the number itself is not large, but because of increasing the length, this number reduces down further.
Right. Yeah, got it. Thank you.
Our end objective is we want to find out this number, this 60 or 100, whatever, based on what is the length of that column. So we should be able to identify first if the column is short or not. If the column is short, the procedure is straightforward. Just multiply the area by yield stress. Now, if the column is slender, then what to do? That is what we are going to get next.
I had a question.
Yeah,
Is the squash load equal to the yield strength of the material?
it is.
Thank you.
Because strength is nothing but the stress at failure, which is yield stress. So when you say strength, the strength can be, in terms of stress or in terms of force. So if you're saying strength is nothing but the stress at failure. The stress at failure is nothing but strength. So since the stress at failure is yield stress, so the strength is Fy. Okay. So this is just experimental setup for finding out the design strength of a short column. Just get a feel of the scale of the reduction in the length of that column. So before it can actually squash, just like a tension member, you can expect a compression member to undergo a significant deformation, but uh, you know, uh, but contraction, and not elongation. Elongation occurs in tension members. So in compression members, you can expect significant contraction before it actually yields. Now the next one is
Before we move to the next one, can you explain the difference between buckling and squashing? I got a little confused.
buckling and squashing. Okay, so let me first explain what buckling is through this slide, and then we, if not, then if there's still some confusion, we can look at both of them together. So buckling or flexural buckling governs the design of the commonly used compression members. So almost all the commonly used compression members fail by flexural buckling because the reason is simple. If you want to make sure that the column fails by squashing only, then you might have to increase the cross section area of the column, and that might shoot up the cost of the column and then the cost of the entire project. So the normal sections or the normal members are provided in typical buildings. Majority of the sections or the design strength of majority of the sections is governed by flexural buckling. Now let us understand what buckling is. Now, again, this imagination experiment. You are holding a steel ruler in your hand and you are trying to compress it. Does it squash? So, before that, does it contract? No, because the amount of load that you're applying is not enough. So, does it squash? Definitely no, because it does not contract at all. But something is happening to it, right? And that something is that it is deflecting sideways. Now, if you're applying a load that is along its length, why is it that it is deflecting perpendicular to that? So, this phenomenon in which there's a deflection which is normal to the axis of the load is called as buckling. So, the load that you're applying is along that length of the member, but the deflection is perpendicular to that. This phenomenon is called as buckling. Now, go back to the experiment and, let's resume that experiment. You notice that the buckling occurs along minor axis. Now, what do I mean by that? So if this is your steel ruler, okay, so you'll notice that it sort of buckles like this, okay, and not the other way around. It does not. So it buckles along the minor axis. So this is the minor axis. This is the major axis. So it does not buckle like this. It buckles like this. So it buckles along the minor axis because it is weaker along the minor axis, and that is the reason why it buckles along the minor axis. So we have a small addition to this. So buckling is marked by excessive deformation, or this failure is marked by excessive deflection or buckling normal to the axis of the load in the plane of weaker principal axis. So this is nothing but buckling. So what is the what what is the what I can say? What is an obvious factor that is causing buckling? The answer to this is length. Obviously, longer the column. For example, now you took a 30 centimeter scale. Now you move on to 60 centimeter scale. It is going to buckle even at a lesser load. So length is an important factor that causes buckling. So the longer the column, the lesser is the value of buckling load. Okay. So now talking about the difference between squashing and buckling. So squashing occurs by deflection, or squashing occurs by deflection in the direction of force. So what do I mean by that? So if this is the original length of the member, um, so let us say if this is the original length of the member, and after squashing, this is the length of the member after it undergoes, and just before it undergoes squashing. So there's a deflection along the line of action of force. Now, how is the force applied? The force is applied like this. So the deflection is in the direction of force. Okay, but if we take the same member, increase its length, and now we apply an actual force on it. So what might happen is the deflection might deflect like this at failure. So this failure is buckling, and this failure is squashing. So do you have the answer to your question?
Yeah.
Okay.
Bhargav, I had a question.
Yeah.
Sorry, I can hear an echo.
From my end?
Yeah, like when I'm speaking. I think it's fine now. Yeah, I just wanted to ask in terms of forcing, how short the column has to be called a short column. How
Yes.
do we decide that?
Yes, that's a very good question. And we are going to try to answer this question in the next few slides.
All
Okay.
right. Thank you.
So
Yeah.
why are we learning all this? The objective is ki, bhai, which is short column, which is long column. Like why? What do I call a short column and why? I need some numbers because before that, just let us take again look at a small experimental setup of flexural buckling, and then we move on to that.
This video shows a slender fixed-ended column being tested in compression. The specimen is a rectangular hollow section made from structural steel. The length has been chosen so that the failure is dominated by a buckling instability. This is primarily a geometric effect. The loading diagram shows a compressive force evenly applied to both ends of the specimen. The testing rig is now starting to apply a compressive force to the specimen. We can see the top end displacing and the column begins to deflect sideways as a result of a structural instability, which is better known as buckling. The profile of the column as it buckles is theoretically a full cosine wave. Note that the column ends do not rotate due to the fixed-ended conditions. The column maintains this shape as it continues to deflect, until eventually material damage takes hold, which distorts the shape. This particular phenomenon is dominated by the elastic behavior, and material effects are secondary but ultimately trigger failure. The graph initially shows a linear relationship between force and displacement. Up to this point, the column hasn't begun to displace sideways. Once the buckling instability is triggered, however, the slope effectively reduces to zero. Finally, after significant displacement, the load carrying capacity begins to reduce, and this marks failure from material effects.
Okay. Now going to her question. So what do we call short and what do we call long? Now, if we look at these two figures, it's easier to say that the top one is short and this is long. But then what is this? Is it short? Is it long? What is it? So it's a relative term, and therefore we need some numbers we need to put some numbers to understand what is a short column and what is a long column. So before putting in some numbers, let us first define what short column is, define what long column is, and then only we can put some numbers on that. So columns are classified as either short or they are classified as long or slender, and then intermediate. Let us try to understand what this means. So any section or any member that fails by squashing, that is, any member that fails by material reaching its ultimate strength, or sorry, any member that fails by material reaching its yield stress is called as a short column. And any column that fails by elastic buckling is called as a long or a slender column. Now we have this word has come up again and again, buckling. But then what is elastic buckling? So in short column, the entire section reaches yield stress. If in a long column, no part of the section reaches yield stress, then it is called as elastic buckling. Now, what do I mean by that?
Can I try to answer that?
Yeah, go on.
So is it inelastic buckling is when the column fails in a way that it cannot be restored to its original state because it's kind of bent and buckled. But in elastic buckling, it doesn't bend and buckle. It simply buckles without bending or distorting way too much beyond the elastic limit.
Okay. So the answer is partially correct. Okay. Now let us just look at this and then see if we understand it completely. So let us say this is a cross section of a column, a rectangular one. So if I say that the column is failing by squashing, what it means is that the entire cross section will have a stress that is equal to yield stress. Okay. just to make sure that we are understanding it visually as well. Let us say we take a slender column. Okay, now a slender column, so this column might buckle like this along the weaker axis. Okay, always remember. So this is the weaker axis. This is a stronger axis. So if it has to buckle, it'll buckle like this. So if it buckles like this, the stress here would not be uniform. So the stress, the compressive stress, might be larger here. See, this is all indicative. Okay, this is only to get to get a basic understanding. We're not getting into the actual phenomenon. This is a very a raw version of what actually happens. So what might happen is this part. So the stress in this part might be larger as compared to the stress in this part. Why? Because this portion is under compression. This is under tension. In addition to the overall compression, because of the moment. So here we'll have, okay, again, let me put some numbers to it so that we are clear about what is happening. So if because of the axial load P, there's a compression C1. Now because of the moment, we have a compression that is say C2 and a tension that is T. So on this side, the compression would be C1 plus C2, and on this side, the resultant force would be C1 minus T. Is it getting too technical? Okay, I think it is. Let's just forget this.
So basically, one side is receiving force and tension, and one is receiving the force, but is also relaxed by the tension that goes to the other side.
Yes, it is. That is what I precisely wanted to say. But nonetheless, so here the stress is uniform, but here the stress is not uniform. Okay, it might happen that the stress looks something like this. But here the stress is uniform, which is Fy, and here the stress is larger here, and then it reduces as we move outwards. Okay, so now what is happening is, in a same section, some portion has a higher stress, some portion has a lower stress. So what might happen is, some portion is reaching yield stress at failure. So some portion is reaching Fy, where the stress here is less than Fy. Okay. Maybe let me just take one step back. Okay. So let us just say that at failure, this entire stress is less than Fy. So no portion of the section has reached yield stress. Such a failure is called as elastic buckling, wherein the buckling is occurring when the entire section is elastic. Okay, so so this stress is yield stress. This stress here is less than yield stress, and even this stress is less than yield stress. Such a failure is called as elastic buckling, meaning that the buckling is occurring when the entire section is elastic. So he rightly said that if you remove that load, what will happen is this buckle shape might go to the original shape because it is still elastic. Now let us look at a third type, which has length something like this. So in this case, what might happen is so some portion. So let us look at the stress diagram. So this portion, the stress in this portion is Fy, and the stress in this portion is less than Fy at failure. So some portion is elastic. So this portion is elastic, and this is not. So such a member is called as such a member is an intermediate member, and the failure occurs by inelastic buckling. Is it too much to take in? See, it's very simple. In a short column, the entire section has yield stress. In a long or slender column, no part of the member has yield stress. And in elastic buckling, either some portion or the entire portion has yield stress, but the failure occurs by buckling. So here, the failure stress is equal to yield stress. Here, the failure stress is less than yield stress. Even here, the failure stress is less than yield stress, but in this case, it is greater than case number 3. There is no buckling, so there's only squashing. The squash load is given by Fy into cross-section area. Here, now, how do we find out the load for a buckled column? So the buckling load is given by Euler's formula, and here the buckling load is given by what is called as modified Euler's formula. Okay, we'll look at what it is later on. Just try to understand the basic classification between different types of columns. Simple. Short columns fail by squashing at squash load. There's yielding. Long columns fail by elastic buckling. The stress is less than yield stress, and the load is found out by Euler's formula. In intermediate, a part of the column may be elastic, the rest of it might be inelastic. The failure is called as inelastic buckling, and the buckling load is given by modified Euler's formula. Any questions here?
Yes. So if a column just simply sort of falls over because of the uneven loading, not because of not really like when one load is way too offset and then kind of just falls over the column.
Okay.
Would that be a really slender column?
What do you mean by falls over?
Like it just kind of it very how do I phrase it? Like if a timber column isn't properly attached to the base and it's just held mainly by its weight, right?
Okay.
Like a massive timber stone column, and the load is offset in a way that kind of just pulls it out of its socket and makes it fall over. So the member is entirely fine unless it shatters and hits the ground. There is no deflection in the member. It has just turned and fallen over due to the seesaw of the load. It hasn't faced any sort of distortion. It just b- angled from the direction of the load. Like the moment was too great.
Okay, I don't understand your question fully, but do you mean to say that what if this is very large, this eccentricity is very large?
Yeah, exactly that. Thank you
Because
for
of that,
phrasing it.
we have a significant amount of movement, and uh, further to that, what? So
No,
if
just
this
that the
is
lateral load is so much more than the vertical load that it kind of just knocks the column over.
yeah,
So that is the form of buckling, right? Or is that just the column falling over?
okay. So that uh, it is not necessary that under this moment the column would buckle. Okay, okay. I sort of now I understand what your question is, and so what you're basically saying is, so if this is a column, say it is a short column, but what happens in this short column is that the moment is significant. So is it that it will buckle only because the moment is significant? So the answer is no, because what might happen because of the moment is there might be a significant stress. Say here on this phase, there might be a significant stress, and the stress on this phase might be relatively smaller. But ultimately, the failure is going to happen when this reaches Fy. So the behavior of the member is not really a function of how much load we are applying. The behavior of the member is a function of how have you proportioned it. Meaning, what are the dimensions, what are the cross-section dimensions, and what is the length of that column, and what are the end conditions. So that is what is going to govern how it behaves. How much load we are applying is not going to govern how it will behave.
Yes, understood.
Could
So
I
the
understand?
eccentricity, yeah, so the eccentricity alone is not enough to knock off a column. The force will also play a part in it.
What I'm saying is that force, eccentricity, moment does not govern how the column will behave.
Yes, exactly. Yes, it still has some yielding force behind it.
Only the material, cross-section, length, and end conditions are going to govern how the. Now let us go back to the first few slides. Only these factors will govern how the member will behave. So this list does not include force or eccentricity or moment, meaning that the amount of load is not going to govern how column will behave. Okay, so if as a person I'm really calm, and if I'm a perfect compression member, so if I'm a short or I'm a stocky column, the amount of pressure that you put on me is not going to change the way I behave. So that's about compression member. So irrespective of what the load is, it is not going to change its behavior. It's going to behave the same way, irrespective of what is the amount of that, or what is the amount of
Yes,
excentricity, the amount of
yes,
moment.
yes. Thank you. I
Yeah.
just want to confirm that because essentially numericals we did last time. So yeah.
Okay. So, uh, any questions here? Like, how much percentage of what I'm explaining are you understanding? It's really important because now we are going to step up. If you think that this was difficult, we are going to step up. So let me know if you've missed anything, you've not understood anything.
I'm
Bhargav,
not
yeah,
sorry.
sorry.
Yeah.
Sorry, go ahead, go ahead.
No, I was saying that I'm not sure about the difference between intermediate and long slender buckling. I can tell you what I've understood till now. So I think in intermediate, basically, one side of the column reaches yield stress, but the other side does not. And in long slender, nothing reaches yield stress, but because the longer side is the overall compression plus the compression of that part, and the shorter side is the overall compression minus the tension.
Okay. So let me put in very simple words and tell me if you understand after that. In short columns, the entire section yields at failure. In long or slender columns, no portion of the cross section yields at failure. And therefore, it is called as elastic buckling because the entire section is elastic. Is this clear?
Yeah.
Difference between short and slender. In intermediate, either a part, okay, or the entire section might yield at failure, but the failure starts by buckling. Okay, now let me go back to this video and just listen to the last few lines that he says.
Initially shows a linear relationship between the column hasn't begun to display. Finally, trigger failure by the elastic behavior to deflect until eventually material damage takes hold, which distorts the shape. This particular phenomenon is dominated by the elastic behavior, and material effects are secondary but ultimately trigger failure.
What happens is the failure starts by buckling, okay, but ultimately either part of the section or the entire section reaches yield stress at failure. So such a member is called as an intermediate member. Okay, so in short members, the failure is by material only. In long or slender members, the failure is by geometry only. Okay, in intermediate, the failure starts because of geometry, but occurs because of material. The final failure occurs because of material. Should I repeat this?
No, I think I got it now. Yeah, thank you.
Yeah. So if you think that this is very confusing, you can, as of now, you can just focus on short columns and long or slender columns because that is what you're going to look at. Okay. If after understanding these properly, you still need a better understanding of this, just let me know. We'll find out a different way of looking at this. So any questions?
Yeah, I have one question.
Yeah.
In buckling, how do we decide on which side it's going to buckle?
It buckles along the minor axis.
No, like that I get, but like for example, like if I see in this like graph, like yeah, like that column, like how do I decide whether it's buckling towards the right or towards the left?
Oh, that way. So you're asking how do I decide if it buckles like this or buckles like this?
Yeah.
So it depends on the load. So if the load is say here, if the load is somewhere here, or if the loading is something like this, then now you tell me how will it buckle.
It should buckle the opposite way.
So if I call it 1 and if I call it 2, you tell
It
me
should
if the
buckle one, I think.
it should buckle 1, right? It's intuitive. If the load is here,
Then it will buckle two.
yeah. Or if you can't understand this way, what we can do is okay. So let us say the load is here, or the load is here. What we can do is we can replace this load by an actual load and a moment, which is P times E, and this is P. So how does this moment act? So this moment sort of tries to deflect the member like this, right? This moment is trying to deflect the member like this. So it will buckle like this.
Okay.
Now, there's something that will honestly tell you that, this particular batch is asking really relevant questions, and that is something that I like about you guys. First thing is you're asking questions, and the quality of questions is really good. So I appreciate that. Someone else had a question? No?
I had a similar question what Fleur had and it got cleared. So thank you.
Okay. So now, last
I
20
have one more question. Like I've
Okay.
uploaded a picture in the chat box. So
Okay.
like that would be squashing, right?
Mm. Is it a hollow? So what section is it?
It's a solid section.
It's a solid section. So, though this is a little bit of exaggeration, but yes, if you're going to reduce the length, the diameter or the dimensions is going to increase it because of the
No,
point
but like
selection.
my main concern was like the curve on both the sides. If it occurs on both the sides, like will that be considered squashing or buckling?
You mean this curve?
Yeah.
That is really not relevant here because, see, okay, let us see if I can answer this. So, when we are talking about a curve, this is the entire member that is buckling. Okay, and what you've drawn is, say, if this is your member, you say that okay, at squashing it happens like this, right? But it does not really happen like this, because under uniaxial compression, the entire member is under a stress that is same. So sorry. So ideally, at failure, your section should look something like this, wherein this is the reduction in the length of the member. But when you're saying what happens when it is actually failing, so we might have something like this, you know. But this is not. This really does not mean that it is deflecting that way. This is just a localized, in concrete it is crushing. It is a local. It is a localized squashing that is happening. It does not mean that the deflection of the member is like this. The deflection of the member is still vertical only.
Okay, so it's basically the length which is being reduced that is being spread out like that.
Yes, here the deflection of the member is like this. In squashing, the deflection of the member is vertical.
Okay.
Okay, no more questions?
Yeah, thank you.
So last 20 minutes, I really want you to focus, because if you understand this, then this topic is over. Okay, whatever we have discussed was relatively easier to this. Just make sure that you listen to me. So now let us, now squash load, it's very easy to find out. We know that squash load is equal to stress times area. Simple. But how do we find out the area for slender column? It's so there has to be theory behind it. Okay, so let's look at the theory behind the behavior of compression. So if it's a short compression member at very low, so this is a little exaggeration. Okay, so what actually happens is, if I have to draw a graph, if this is my x and y axis, what happens is it's very close. Then there's a sudden, when the stress reaches Fy, there's a sudden increase in the strain, or there's a sudden increase in the deflection. So at very low values of axial load, there is no visible deformation either in the axial direction or in the lateral direction. And the entire section experiences a stress that is equal to force upon area. Now, a significant deformation is only possible when the stress reaches yield stress. And the load at which this happens is called as squash load. Simple. So this was about short members. Now, what about slender members? Slender members behave something like this, wherein the material is not getting a chance to reach yield stress. Okay, before the material reaches yield stress, it starts buckling, and as soon as it starts buckling, the curve sort of takes an exit from its ideal behavior, and it goes like this. And this is what we saw in the experiment as well.
And to display sideways.
You see this reflection curve before it can reach yield stress. Now, what is the yield stress here? I think we displayed the value. Yes,
the length has been chosen so that the failure is displayed sideways.
If you look at this number, it's way less than 250 even before 75. It's 275. If you look at this number, it is way less than 275, somewhere around 80. So what happens is, in a slender member, the material never gets a chance to reach its potential. Before that, failure starts occurring, and you will expect the behavior of a slender member to be something like this. Okay, So the maximum load that a slender member can take is called as Euler critical buckling load. Just give me a moment. So the maximum load that a slender compression member can take is called as Euler critical buckling load. Now, Euler is the scientist who gave this formulation, and therefore it is named after him. So let us look at what this formula says. So this PCR, or the critical buckling load, is pi square EI upon KL square. Do you remotely remember ever heard of this formula before? Is it a no? If that's a no, then let me tell you it's not possible because you've studied Fourier structures 1 and 2. So 1, 2, 3, 4. So definitely you've heard this. You've come across this formula. So Euler's critical buckling load is pi square EI upon KL square. Let us look at each of these terms. So E is the modulus of elasticity of the material. I is the moment of inertia. L is the unsupported length of the member. And K is the effective length factor. And therefore KL is the effective length of the member. Okay, have you heard of this term? Effective length?
Yeah, last
Yes,
year
yes.
we
Okay. I appreciate your honesty. So the formula is PCR is equal to PCR is pi square EI upon KL square. Now, if I want to understand what is the critical buckling stress, so FCR is equal to PCR upon A. Stress is equal to force upon area. So you just divide this by area. So I can write this as pi square E I upon A, and this entire term upon KL square. Does I upon A mean something? So if we go a little back, we know that radius of gyration is equal to square root of I upon A. And therefore, I upon A is R square. So I can rewrite this as pi square E into R square upon KL square. Now I can rewrite this as pi square E upon KL upon R square. Now I can rewrite this as pi square E upon lambda square. And lambda is nothing but KL upon R, which is called as slenderness ratio. So PCR is equal to pi square EI by KL square. FCR is equal to pi square E upon lambda square. Okay, so you have to remember at least the first one. So PCR is equal to pi square EI by KL square. Okay, lambda is nothing but the slenderness ratio. Heard of this term before? I'm sure you have. Slenderness ratio is KL upon R. Is it clear up to here?
could you repeat what K?
Sorry.
Nothing.
Okay. So at least now we sort of have start as to how a compression member behaves. If it's a short compression member, we can expect it to behave like this. If it's slender compression member, we expect it to behave like this. Okay. So from this formula, where is it? Yeah. from this formula, FCR is equal to pi square E upon KL square. Now pi is a constant and E is also a constant. The only thing that varies is lambda. So from this formula, we can say that FCR is inversely proportional to lambda square, right? So let us try to plot a graph for this. FCR is inversely proportional to lambda square. So if I plot FCR on the y-axis, lambda on the x-axis, my graph will look something like this. This is the graph of x is equal to 1 upon y square. So if this is FCR and this is lambda, this is how the graph will look like. Now, looking at the formula, does it mean that as lambda tends to 0, FCR tends to infinity? Meaning that if your column is very slender, it can take infinite amount of load. Is that correct? A simple question. If, say, the column is very short, 2 mm column, does it mean that it can take infinite amount of load? Come on, guys, it's not a very difficult question to answer. Can any material take infinite amount of load?
Practically no, but like theoretically it could because it's like so short.
No, just because the formula says so, it might happen because of this
Column that's at height 0, yeah.
Column whose height is 1 mm. So according to this formula, it might take infinite amount of load. But
No, column that's height 0. Right.
sorry?
Wouldn't that be a column of height 0, not 1 mm? 1 mm would still.
So okay. So 1 upon 0 does not mean anything. So whenever we are talking about limits, we just say that it tends to 0. So a column of height 1 mm is 0 as compared to a column of height 3 meters. Okay. So when we talk about limit, we always talk about tends to 0 or tends to infinity. So it is getting close to 0. It's not, because when it becomes 0, it would not make any sense. FCR would not make any sense. So what basically this formula says is that as lambda tends to 0, FCR tends to infinity. Theoretically, that is what the formula says. But we are forgetting something, that this is for a slender column. Okay. Irrespective of what the column type is, there is always an upper limit of FCR, and that limit is equal to Fy. Why? It's very simple. Be the column slender, be the column short, be it intermediate, it can never exceed yield stress, irrespective of the type of the column that is. Okay, so this is an upper limit for FCR, meaning that there is this upper limit that the column can never cross FCR. That FCR can never cross. It is Fy. So this is the curve that I get from here, and this is the curve that I get from here. So now I have got a sort of a failure envelope, which the column, if the column crosses, then it has failed. If I draw this graph again, this is my curve. Okay, and this is if I extend this curve further, it might have, forget it. Okay, so this is a failure envelope. FDR, and this lambda. Okay, so there are two components of this curve. This is that of the slender column, and this is that of a short column. So we now have a transition point. So if I find out the lambda for this. So any lambda that is less than this will behave as a short column, and any member that has a lambda greater than this will behave as a slender column. So now we can put a number on the slenderness ratio and then compare our slenderness ratio with that number. If our slenderness ratio is less than lambda p, we say that it's a short column. If our lambda is greater than lambda p, then we say that it's a long column. So it is a slender column. So let us go back to that graph. So from this formula, I'll just explain this again. So from this formula, it is clear that phi is constant, E is constant. So FCR is inversely proportional to lambda square. FCR is inversely proportional to lambda square. But there's always an upper limit of FCR, which is Fy. So if we sort of merge these two curves, we get a final curve which looks like this, ABC. This is a failure envelope. So our stress will always be within this curve. Okay? The transition at which, or the point at which the transition occurs is this point P. And the slenderness ratio corresponding to point P is represented by lambda P. Any column that has a slenderness ratio of less than lambda P is a short column. Any column that has a slenderness ratio greater than lambda P is a slender column. So let us try to find out lambda P for mild steel. So if for mild steel, Fy is equal to 250 megapascal. So in this formula, just plug in Fy is equal to 250. What is the value of lambda P that you get? I hope you already know the value of phi. The value of P is 2 into 10 to the power 5. If you plug in these three terms, the value of lambda P that you get is 88.85. So for mild steel, okay, this is a function of only the grade of steel and nothing else. Only the grade of steel. So for mild steel, any column that has a slenderness ratio of less than 88.5 is a short column, and any column that has a slenderness ratio of greater than 88.85 is a slender column. Question. Okay, moving on. So an easier way, to represent this curve is when we normalize it. So normalizing means that, this we just turn this curve into unit lengths. For example, here the units are megapascals. Here it's a slenderness ratio. It's just a ratio. So when we normalize this, we divide this entire all the y coordinates by Fy. We divide all the x coordinates by lambda p. So the curve still remains the same, but this point Fy upon Fy is 1. And now this curve, instead of FCR, it becomes FCR upon Fy. And this curve, we divide it by lambda p. So lambda p upon lambda p is 1. This becomes 1. And now the remaining portion.
Sorry, Bhargav, I had a doubt earlier, but I didn't want to interrupt you. My mic wasn't unmuting when you asked the questions.
Yeah.
But when we are talking about these columns in theory, we aren't considering any loads that could be happening other than the structural load, like wind load and
Wind load is
earthquake
just
loads, right? This is,
wind,
we're
earthquake.
just looking at the structural load, right? The dead load, so to speak.
No. We are looking at all loads. So P is the maximum of all the loads that is occurring.
So it's the unified vector of all of them.
Yes, it is. It is the governing load combination. Okay. So we want to normalize this curve, meaning that now we want to divide lambda by lambda p. So what is lambda? If we look at this formula, yeah, this one. So lambda is pi square e upon fu का square root because this is lambda square. So what is lambda p? You just replace FCR. So this is FCR. Sorry. So you just replace FCR by Fy. So pi square e upon Fy. So the similar terms get cancelled, and this is equal to square root of Fy upon FCR. That is what can be seen in the curve. So now we normalize because we just want to reduce the number of factors that we see, in that curve. Now here, everything is only in terms of Fy and FCR, and there are no other factors. See, the intent is not to understand what normalizing is. The intent is just to get a design curve. We have represented the same thing, which was earlier, a plot of stress against that tendency. So we have just normalized it. Okay, so just understand this curve because we want to, look at a curve in the code that is similar to this code, that is similar to this curve, and that is the reason why we looked at this line. Okay, so this is the final output that we get. Now this is a curve that the stress in the column should always be lesser than the stress that is represented by this curve. I think we have already reached our limit, but this concept is really important, and I did not sort of wanted to, keep it hanging. But nonetheless, I'll just try to explain it in 2 minutes, and we can pick up again in the next lecture. So Euler gave this formulation in 1750s. Okay, but this was not considered in the actual design of columns, because it did not match with the actual experiment results. So in actual experiment results, we never got a curve like this, and therefore Euler's design was not considered in the design. Euler's curve was not considered to actually design columns for a long period of time. Okay, and then eventually, after about 200 years, after a lot of study, we realized that this is a curve for a perfect column. But actually, there are a lot of imperfections in columns that are actually built. We talked about a few imperfections before. That the column might be initially crooked, or there might be a certain accidental loading that we're not accounting for in analysis. Okay, or there might be, when the column comes out of the mill, there might be some residual stress in that column. So there are a number of imperfections in that column. And again, an important, important factor is that for this formulation, it is considered that the column is an individual member that is getting loaded. But in actual practice, you have hundreds of such columns tied together, and you cannot expect the column to behave as if it is an individual column. Okay, it is so the behavior. So it's a structural response first, and then a member response. So it's a combination of the structural response and the member response. But here we say that the column is only a single member that is being loaded. That practically never happens. So for a long time, we could not put all these factors together. And that is why we say that this theory does not make any sense, because in actual, we don't get such results. So in 1950s, 1955 to be specific, about 7 European countries came together, and they formed a panel to solve this issue once and for all, because there were a number of approaches in different parts of the world that were being followed. So we needed a unified solution to this. So all of these 7 countries, people from all of these 7 countries came together, performed thousands of experiments. Okay, and finally they came up with 5 curves that could cover all the columns and all these imperfections. And if we follow this curve, perhaps we are reaching closer to how an actual column is going to behave. And these curves are what is adopted in our Indian code. Okay, So we looked at this curve, FCR upon Fy. Now, since we are talking about design, in code it is referred by FCD. So it stands for the critical design load. Fi is the yield stress, and this is lambda. So this is basically lambda bar, which is Fi upon FCR to the power 1 by 2. So this Indian code sort of, adhered to 4 curves. The original committee gave 5 curves, and then different countries adopted 3 curves, 4 curves, 5 curves, depending upon what they felt comfortable with. British adopted 4 curves, and therefore, referring to that code, we also adopted 4 curves. So now these 4 curves are these 4 curves have the responsibility of covering all the columns in the universe. So if you just know if your column falls in category A, B, C, or D, you can just find out what is FCD that the column can take. Okay, and these curves are sort of take care of all the practical imperfections in addition to the perfect theory that we looked at. I said at the start of the lecture itself that designing a compression member is extremely complex because there are so many factors involved. Now, if we give a 1 kilometer formula for designing a column, it is not going to be easy for designers, right? So the objective of the code is to squeeze the information as much as possible, and they've done a great job by squeezing all the imperfections, all the possibilities into only 4 curves. So if you know the slenderness ratio, you can only code this curve and know the value of FCD. It's that simple now. And that is what we're going to do in the next lecture. We'll just see how to find out the slenderness ratio and use these curves. We'll see how to categorize our columns as A, B, C, or D, and then use these curves to find out what is the value of FCD. So I understand that, all the, concepts that I've taught today might not be clear to you, but I'm sure that you must be clear of the objective that we are trying to achieve here. And then we'll sharpen the concept as we go on. The objective is to find out the load at which it fails. How can we find that? By finding out the stress at which it fails. If you multiply stress by force, we'll automatically get the load. In order to find the stress, we are looking at this curve because x-axis is something that we know. X-axis is slenderness ratio. So from the slenderness ratio, and if we know the type of curve, we can just go to this and we can just find out what is the so what we can do is, if we know what the slenderness ratio is and if we know the type of curve, say it's A, so we only have to go here, right? So we only have to go here. We'll know this value, say 0.47 times of Fy. This is my value of FCD. So my design compressive strength, say PCD, is equal to FCD multiplied by area, and there's going to be some safety factor. So we'll get the value of PCD or PD. I'm not sure what is. Yeah, it's PD. So PD is equal to FCD times of area. That's how we get it. It's that simple. Okay, so I just want you to give some time. I just want you to invest some time in understanding what we learned today. Go through the presentation. If required, refer to some books. I've already given you the set of books that you can refer to. Look at the code. By the way, this is IS 800-2007, which is a steel code. Look at the code. Look at these codes. It is, you refer to the index. It's section 7 of design compression members. That sort of gives this curves. In the next lecture, we are going to look at the code. We are going to look at how we classify this and how do we solve this puzzle of finding out the critical buckling load. Any questions here?
I had a question.
Yeah.
The slenderness ratio we used, lambda p,
Yeah.
you said that anything lower than that value would be short and anything bigger than that would be long. What
Yes.
if that is the slenderness ratio? What category will it come under?
What if?
What if the slenderness ratio is lambda p? In what category will it come under?
It's short. That's the upper limit for short column. Okay. Now, to clarify one thing, if the slenderness ratio is 88.84, the column is a short column. If the slenderness ratio is 88.86, is it a slender column? Yes and no. If we strictly say that, look at the numbers, maybe yes. But is it going to actually be as a slender column? Probably no. Because we're not into a physics experiment. This is we are talking about real, practical columns. And by an increase in the slenderness ratio of 0.01, it is not going to change its behavior. We are just trying to put a line that we want for our convenience. Okay. So even if it's 89, is it a slender column? Theoretically, yes. Practically, maybe no. It's still a short column. So we're just putting some numbers for our convenience. But if the slenderness ratio is 150, then it is a short column. Definitely no. It's a slender column. So you perceive these numbers this way. It's not an absolute limit. If 88.86 is a slender column. Theoretically, yes, but practically it's still a short column. Might still a short column.
Thank you.
Bhargav,
Yeah.
so when we're looking at a column that's larger at the bottom and more slender at the top, like an obelisk or a spire usually is to accommodate for height.
Mm-hmm.
So even columns that kind of flare up downwards to sort of spread out their load, how do you take the slenderness ratio for them? Do you take each cross section individually, or is there a way to take them as pyramidical or conical fracture?
You just find out. Okay. That for that we'll have to look at how does the bending moment and the axial force vary along the length of that column. What I'm saying is you have to look at the bending moment diagram of that column. And if you notice that the critical bending moment occurs somewhere in the middle, meaning that where the section is a normal section, it's not flaring out. For that, you'll have to check it at the normal section. And if you find that the bending moment is, the largest value of the bending moment occurs at the bottom where it's flaring, perhaps you look at that section for carrying the slenderness ratio. But such conditions are not typical. We are talking about typical conditions that we can apply to any typical column. So if we cover more than 90% of the cases, I think we are good to go. Others, we can do special studies and find out.
Yes, indeed, of course. Thank you.
Yeah. Any more questions? Good. So I think you just like me, even you feel that there's a strong reason for you to go back to this presentation and study everything that we have taught. There might be very less content on these slides, but there are a lot of concepts that we've talked about. So reading the presentation is a must. And if there's still any doubt, go back to book and just read these concepts. So with this, we'll stop for today. We'll meet again on next Saturday, same time, and hopefully with a better understanding of computation members. There'll be no test in the next lecture. We'll try to wrap up computation members with a couple of numericals. Thank you for your time and your patience.
Bhargav, just a minute.
Yeah.
I mean, last time we spoke about we're going to have the midterm marking, and then for those who missed like some tests due to some reasons, will there be a test again?
Just a moment.